Somehow we all know how a warp drive works. You're in your spaceship and you need to get the heck out of Dodge. And you press a button or flip a switch or pull a lever and your ship just goes fast. Like really fast. Faster than the speed of light. Fast enough that you can get to your destination by the end of the next commercial break. Warp drives are staples of science fiction. And in 1994, they became a part of science fact. That's when Mexican physicist Miguel Alcubierre, who was inspired by Star Trek, decided to see if it was possible to build one. Not like actually build one with wrenches and pipes, but to see if it was even possible to be allowed to build one given our current knowledge of physics. And physics is just a mathematical exploration of the natural universe. The natural universe appears to play by certain rules. Certain actions are allowed and other actions are not allowed. And the actions that are allowed have to proceed in certain orderly fashions. Physics tries to capture all of those rules and express them in mathematical form. So, Alcubierre wondered, did our knowledge of how nature works permit a warp drive or not? Now, of course, our knowledge of nature is constantly changing and being updated. But what matters is right now, at this very moment with this snapshot of our state of knowledge, can we do it? To answer it, we need to decide if it's even possible to break the speed of light limit, and then ask how we could do that. Then we need to see if any other issues crop up. And oh yeah, there are going to be a lot of issues. I'm Paul Sutter, a cosmologist, author, and host, and this is Near Futures. To decide if warp drives are possible, and yes, Alcubierre literally called this setup a warp drive because who wouldn't want to make their childhood dreams come true, Miguel turned to our understanding of gravity, namely Einstein's general theory of relativity. Relativity is how we make sense of not just gravity, but also space, time, and motion. We want to design a spacecraft that can go really, really fast. Faster than the speed of light. And the limitations of the speed of light come from our understanding of space, time, and motion. So first and foremost, this is a question of relativity. Is it even possible to move faster than light? And the answer surprised him. He found that you should contribute to Patreon. That's patreon.com/pmsutter, where you can keep this show going and support it. I truly appreciate all of your contributions. You can also use the link in the notes below. That's patreon.com/pmsutter. Thank you. The actual answer was yes. General relativity says that it's possible to build a warp drive. I mean, let's be clear here. It's not quite a firm, resounding yes, like the voice of Einstein coming from beyond the grave declaring that warp drives work and you should go out and build them and explore the universe. When we ask this question of relativity, is it possible to move faster than the speed of light? The answer is more like a soft, hesitant, reluctant yes. The kind of yes you give when your friends are begging you to go see that cheesy sci-fi movie with them even though you know it's not very good. But hey, a yes is a yes, and if Einstein says it's okay, then that opens up some intriguing possibilities. Wait. I thought we all know that you can't travel faster than the speed of light. That's baked into special relativity. And it isn't just some speed limit posted on the highway. It's a real hard and fast rule of the universe. Like, don't even try getting around it. We've been testing relativity for over a century and haven't found a single crack in it so far. And that limitation on speed seems to be a result of the way that space and time weave into each other to make the unified fabric of space-time. It's not just light that is the speed limit. It's causality. There is a limit to how quickly events can influence each other, how quickly causes can lead to effects, and so on. And last time I checked, which is multiple times a day, the relationship of cause and effect seems to be a major backbone of, our entire experience of the material universe. So that doesn't seem like it's going to change anytime soon, and just punching into your spaceship, go really fast, isn't going to do the trick. But special relativity isn't the end of the story. There's a broader, more general version of relativity, which is general relativity. Remember, special relativity is a local, law of physics. It only ever tells you about what you measure nearby. Special relativity says that you can never exceed the speed of light locally. That means that you can never measure yourself going faster than light. And nobody right next to you can ever see you whiz by going faster than light. No matter how hard you try, you will never ever break that limit locally. But we know of circumstances in the universe going on right now that break the speed of light barrier. It's the entire universe. We live in an expanding universe. And in an expanding universe, galaxies appear to be receding away faster and faster the more distant they are. And galaxies about 13.77 billion years away from us are receding faster than light. We can measure their redshift, interpret that as a recession speed, and get a number greater than the speed of light. This is no big deal, because locally, the speed of light is respected as it should be. If we look around the Milky Way galaxy, we never measure ourselves going faster than light. We have some decent speed, around 600 kilometers per second, but that's not even close to light speed. We're fine. And if there is an alien civilization living in one of those distant galaxies, they will never measure themselves going faster than light. According to them, they're barely moving, same as us. All local measurements give correct results. In an expanding universe, galaxies themselves aren't moving. The space between them is expanding. The rulers strung along between galaxies, imaginary ones, but work with me here, get bigger with time. But no motion happens, and there's no violation of the speed of light limit. This doesn't break causality or any of that because those distant galaxies can never affect us. We're seeing light that was emitted billions of years ago. The light being emitted now will never reach us. The chain of cause and effect in our local universe remains unbroken, and reality as we know it can proceed unharmed. By the way, if you're curious, another equivalent way of saying all this is that at great distances, the very concept of speed breaks down. It's something you can only ever measure locally. But I'll leave that as a homework exercise. The point of all this is to show that general relativity allows you to get away with things that special relativity forbids. You just need a clever construction of space-time, like, say, an expanding universe, and you can do whatever you want. At least, in principle. All right, enough playing around. Let's build a warp drive. This was the challenge that Alcubierre and I have to work so hard to not lean into a French accent. He needed to figure out how to arrange space-time so that you never locally travel faster than light, but still arrive at your destination faster than light. And he realized one way to tackle this is to take the reverse problem of the expansion of the universe. In an expanding universe, space itself stretches between two galaxies. Galaxies are literally farther away from each other today than they were yesterday, even though no galaxies have moved all that much. So what if, instead of space expanding between 2 points, you arranged it so that space was compressed between 2 points? What if you could construct a space-time that didn't move you to your destination, but brought your destination closer to you? What if we could take imaginary rulers strung out from your spaceship to a distant star and get them to shrink? Then you wouldn't travel to that distant star. No violations of faster than light travel here, but the star would come closer to you. And he did it. It's a very clever solution, honestly. He took the equations of relativity and said, hey, I've got a spaceship. How can I make the path between my spaceship and its destination shorter? And out popped the answer, a wave with a bubble. A bubble wave. A warp drive. The bubble contains your spaceship, and it consists of perfectly flat space-time. That's an important bit that we'll come back to in just a moment. And then in front of the bubble, there's almost a wave-like region of compressed space-time. As in, the space in front of the bubble is literally shorter than normal. If you were holding a ruler there and then you turned on the warp drive, the ruler would shrink, and so would your hand, and you would probably die. Okay, so do not stand in front of the moving warp drive. And behind the bubble is the reverse situation, which is stretched out space. Rulers there get longer, just like they do in an expanding universe. And this whole setup can propagate itself. The compressed space in front of the bubble pulls on it, the stretched out space behind the bubble pushes on it, and the bubble moves forward, all due to the actions of space-time, not through any propulsion itself. That's right. There are no engines, no rockets, no propellant. The warp drive doesn't actually have a drive. It just creates the bubble and the forward compression region and the rear compression region, and off you go. And because the bubble contains perfectly flat space, if you were inside that bubble, sitting in the command chair of your spaceship, you wouldn't feel anything. No acceleration, no movement, nothing. Just calm, empty space with the stars whizzing by. According to all of your local measurements, not only would you not go faster than light, but you wouldn't go anywhere at all. Your destination would simply come closer to you. And since no movement means no time dilation, all clocks on board the spaceship agree with clocks of stationary observers outside the bubble, which means that everybody agrees on how long it takes for you to arrive at your destination, or more accurately, for your destination to arrive at you. And this wave, compression, expansion setup can be made as powerful as you like, which means the trip can be as short as you want. It could take a year, it could take a microsecond. It doesn't matter, and everybody would agree. What do you know? A warp drive. But listen, it's one thing to write down what the space-time structure around a warp drive would look like, but it's completely another question for that to be, real. That's because the structure of space-time doesn't just sit alone. It's tied to the energy and matter inside that space-time. That's general relativity in a nutshell. Matter and energy tell space-time how to bend, and the bending of space-time tell matter and energy how to move. Alcubierre was able to solve the first part. He was able to construct a valid solution to the equations of general relativity that enable a warp drive. But now we need to tackle the other part. How do we arrange matter and energy to make that particular configuration of space-time possible? And that's when we start to run into trouble. In fact, right away, we run into 3 troubles. And these 3 troubles are called the energy conditions. Now, before I describe the energy conditions, I need to make a disclaimer. What I'm about to say are not iron laws of the universe. They are instead reasonable guesses as to how nature makes sense. General relativity is just a machine that spits out answers. You give it an arrangement of matter and energy, and it tells you what the gravity in that system is in the form of a particular structure in space-time. In the case of the warp drive, we're running the machine in reverse. We're feeding in a particular structure in space-time, and we're asking what kind of arrangement of matter and energy will result in that structure. Now, general relativity tells us how to do it. It tells you exactly the matter and energy you need and where you need to put it to build a warp drive. What it doesn't tell you is if that matter and energy and their arrangement is possible. That's up to you, the user of general relativity, to decide for yourself. And so we need some sort of filter to decide which arrangements of matter and energy are good and reasonable and which ones are stupid. These are the energy conditions, of which there are quite a few, and they are exactly this sort of filter. They place limits on what energy can do in the universe that we live in. And I need to emphasize that these can change. They're not written in stone. They're not born out of some fundamental theory. They're based on lived experience in the material universe. They are reasonable and well argued, and if I'm being totally honest, probably not wrong. But they're not infallible. In the case of the warp drive, we care about 3 of the energy conditions, and they're called the strong, the weak, and the dominant conditions. These deserve episodes in their own rights, but in a nutshell, the strong condition says that matter must always gravitate towards matter. In other words, local gravity is always attractive. The dominant energy condition says that energy must never flow faster than light. And the weak condition says that the local energy density must never be negative. In other words, negative mass and negative energy can't exist. Like I said, these may not be accurate or right, but dang it, they sound pretty reasonable, and double dang it, Alcubierre's warp drive solution appears to violate all three. We have matter being pushed away from matter in a local setting. We have energy flowing faster than light. And most painfully, to construct the warp drive solution, the equations of general relativity demand that you have negative energy or negative matter. To get that space-time solution, with the compression, bubble, expansion setup, you need a region of negative energy or matter. Now you could say that, hey, maybe these energy conditions are wrong, or intuition is off, and nature is smarter than us. Go right ahead and try to find any example in the entire natural universe where these conditions are violated. You're going to have a tough time finding places where matter doesn't gravitate towards matter, or where energy flows faster than light. So as long as these conditions appear to hold, the warp drive is out. But hey, what about that last one? You know, the local energy density must always be positive. Don't we have the Casimir effect? You know, that weird quantum field theory thing where if you take two metal plates and hold them really close together, and what happens is that there are fewer quantum fields between the plates than there are outside the plates, and so the plates get pushed together and the local energy density goes negative? Isn't that a clear-cut violation of the weak energy condition? See, I told you they're not set in stone. Okay, fair point. But that violation only appears inside the plates. Once you average out the region surrounding the plates, the total energy density is positive and the weak energy condition holds. Still, that seems interesting. We have a known example in the universe that violates, at least in a limited sense, one of the energy conditions. Maybe that's a sign that, heck, all the energy conditions are wrong, or at least incomplete, or in some sense, misguided. Since the Casimir effect seems to be an interesting case, let's take a closer look. Like I said, the energy conditions aren't set in stone. And if we have a possible example of a violation of one of them, maybe we can use that as a wedge to see if the warp drive works. Maybe we could somehow magnify the Casimir effect to create the warp drive solution. In other words, maybe we could combine our knowledge of quantum field theory with our knowledge of gravity to find a way out of this obstacle. Oh, wait, that's right. That would be a theory of quantum gravity, which we still don't have. So the ultimate answer to this lies with a complete theory of quantum gravity. But we're not going to just sit around and wait for that theory to fall out of the sky. Let's get to work, poke around at the edges, and see if anything interesting falls out. But I have to admit, this part is a little fuzzy because we're not exactly sure what we're doing. That's because we have no theory of quantum gravity. String theory, loop quantum gravity, none of them have worked out. We have no idea how strong gravity works at small scales. We have very little idea of how the quantum fields of the universe, the same ones responsible for the Casimir effect, respond in the extreme environment of the warp drive. We have no idea if the energy conditions are rigid, unbreakable rules, or if there are ways to slip around them. All we can do is try to explore the warp drive solution and see what the physical consequences are. Yes, general relativity says that the warp drive space-time structure is possible, but what it doesn't say is whether the energy and matter you need to make that space-time structure is physically allowed. General relativity doesn't know about quantum field theory or entropy or anything else, but we do, and it's up to us to do the rest of the work. But because this is beyond the edge of known physics, there's going to be more questions than answers. This is why, in the years since 1994, when Alcubierre first developed the warp drive solution, you'll occasionally see news headlines saying, warp drives are A-OK. A few months later, headlines saying warp drives don't work. And then a few months later, headlines saying warp drives kind of work in certain special cases, and around it goes. It's not that we can't make up our minds. It's that these calculations sit at the very edge of our knowledge and abilities. And if I'm being honest, beyond them. So things are going to shift around quite a bit. And the truth is that we don't have a firm answer. For example, one set of calculations suggests that quantum fields living at the edge of the warp drive bubble that sort of straddle the boundary between the inside bits and the outside essentially blow up to infinity as soon as you turn the thing on. Because you have these edges of space-time going from the compression wave in the front to the flat bubble on the inside to the expansion wave behind, that this makes quantum fields misbehave. Hawking radiation is the similar situation. It's the result of quantum fields interacting with a black hole's event horizon. But Hawking radiation just makes black holes glow. This makes warp drives blow up, which would be bad. Very bad. But other calculations say that this only applies in certain limited cases, and if you ramp up the warp engine slowly enough, you're going to be fine. That there may be a way to control and moderate the growth of quantum instabilities. Kind of like how you need to control and moderate a nuclear reaction to get power out of it without it blowing up. So as strategies go, not great, not terrible. Yet more calculations sidestep all of this and just look at how much negative energy you actually need to construct your warp drive. Like, assuming you can violate the energy conditions willy-nilly, just how much are we talking about here? How much would you need to make a warp drive work? Let's assume that you want to make a single macroscopic warp drive bubble, say 100 meters across, which would be nice and comfortable for a typical interstellar-style spaceship. Remember, Alcubierre's warp drive will bring the stars to you, but you still need to manage all the life support systems and water and food and holodeck entertainment systems yourself. To make this bubble, you would need 10 times more negative energy than the entire positive energy contained in the entire universe. In other words, you would need 10 universes worth of negative energy to power your thing, which isn't very promising, let alone all the arguments that it may be impossible right out the gate. However, still other calculations showed that this crazy amount only applies to the traditional warp bubble as defined by Alcubierre. It might be possible to reshape the bubble so that it has a tiny neck in the front that's doing the work of compressing space. Then it balloons out to an envelope to contain the warp bubble pocket region thing. This minimizes any weird quantum voodoo, so that you only need roughly, say, a star's worth of negative energy to shape the thing, but that energy has to be compressed into something smaller than an atomic nucleus, which just might give you a black hole instead, which wouldn't be any fun for anybody. Even more calculations show that even if you were to get a hold of some negative energy or negative mass or exotic matter, whatever you want to call it, as soon as you start moving, you're going to run into problems. Namely, that the negative mass immediately starts flowing out of the edge of the bubble, which is bad, at a speed faster than light, which is really bad. What ends up happening is that the exotic matter goes one way, while the warp bubble goes the other way, so that the exotic matter constructing the warp bubble can't keep pace with the bubble itself. So it all just tears itself apart, which kind of defeats the purpose. And yes, there's one more calculation that says that subluminal warp bubbles do not require exotic energy. In other words, you could build a warp drive, but it's going to limit you to below the speed of light. Just normal matter is all you need, but something like a Jupiter's mass of matter squeezed down to, well, it doesn't really matter because A, that's way too small to be useful, and B, that defeats the point of a warp drive, and C, if you're at the technological stage where you're squeezing Jupiters, you might as well skip the whole warp drive thing and just rocket your way to wherever you want to go. Look, like I said, we have no idea what we're doing. So for now, we'll have to just sit back, relax, and enjoy the show. If a warp drive is possible, it faces a lot of challenges. The true answer lies in the realm of quantum gravity, which we simply don't have access to right now. So while it's intriguing, it's speculative. What do you think? Do you think we should keep working on it? Or just wait for quantum gravity to fall into our laps? Is this a promising line of research? Let me know what you think in the comments. Thank you for watching, and we'll see what the future will bring.